this. All right, state the definition. An element is called a quadratic residue mod n if that element is congruent to square of an integer where that element is coming from group of units. To make the answer easier, the set of such a quadratic residue is denoted by Qn. Un, by definition, Z mod n star, but they begin to abuse notation and write 3 is a Z mod n star. The correct notation is that 3 bracket is in Z mod n star, right? But they sometimes begin to use 3's in Z mod n star. So you have to understand that part. Forgive them. All right, here's an interesting thing, two things here. What we are learning in this section 7, chapter 7, is the solvability of this equation. Whether given A, is this quadratic residue or not? Is there an S in there or not? That's a solvability question. If it is solvable, of course we want to actually solve it. If it is a square root of something, then what is it? If you're a square of something, what is that number? That's a different question. It is not in here. It's usually not the standard part of a elementary number theory. But it's out there. The algorithm is not neat. It's long and not difficult, but it is long procedure. So here we only focus on the solvability. I give you 5 mod 275, and you determine whether it's a quadratic residue or not, right? So that's a solvability. And they found a beautiful algorithm. The algorithm that works like Euclidean algorithm. Factoring takes 2 years. Euclidean algorithm doing like 5 minutes. That comparison is happening again. If you just go ahead and search all the things, square it until you hit that A. If you didn't hit it, quadratic non-residue. If you hit it, quadratic residue, right? That will be the first algorithm come to our mind. That'll take a long time, and they're bragging that we have the fantastic algorithm, and that's what the section's about. Solvability only. But again, it all boils down to Chinese remainder theorem. If you want to see the square in here, you have to look at each individual part. It turns out it's just sufficient to look at Z mod P. So it's all about finite field. In the finite field, given a non-zero class, can you tell me that is a quadratic residue or not? So I want you to challenge yourself with this problem, probably exercise number 1. All right. Finite field, star. How many elements are in FP star? P minus 1, right? We're mapping this one to QP. Who knows what QP is? Quadratic residue, right? In that FP star, quadratic residue. Given by x is x squared. Is this well defined? How do we know it's well defined? Because we squared it, right? Obviously, if you square it, it is a quadratic residue, right? So our codomain is well defined. That's what I meant. It's well defined. There are kind of two different meaning of well defined. Here it's very simple meaning. Our codomain is correctly set up. What does it say? 2-to-1 map. So that means you have FP star and you list them 1, 2, all the way up to what? P minus 1, right? So if you square that 2, where does that go? 4, right? But there's another element that's going to go to 4. So the 2 distinct elements go to 4. And there's nothing else. Only 2 elements will go to 1. That is called 2-to-1 map. Only one element to go to 1. That's 1-to-1 map, right? So every element in here, there will be 2 elements, 2 distinct elements. That's 2-to-1 map. Can you prove it? So that's your exercise number 1. First sentence. Prove it. A simple proof. It may help or not. This information. That it's a simple proof. So let me help you at the beginning. Given A, in QP show x squared lambda in A has exactly two solutions. In FP star. All right, this outline makes sense. It's not a proof. It's a suggestion. Is this gonna that makes a proof, right? Given an element in the QP, for sand, this is solvable. When it's solvable, it has exactly two solutions. Right. However you wrote it, kind of makes sense out of it. First of all, A is a quadratic residue, right? That means there is a number or element in FP star, so S squared equals A. So I know it has one solution, right? So if you divide that by one solution, you can see that, oh, there must be another solution. Or you can look at it this way. If S is a solution, is a negative S automatically a solution as well? Because if you square it, negative 1 becomes positive 1, S squared is still A, right? So S and negative S is always a solution. It's like square root of 4 plus minus 2, just like that, right? You just have to show that S and this T, if T is negative S, they're never equal to each other. If you set it equal to each other, it's 2 times S, right? How can the 2 times be 0 if everything is coming from FP star? They never 0, right? As long as P is not 2, odd prime. Yeah. Question? Yeah. hmm That's right. Yeah. Right. You're right. 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 Here's the same thing that if that statement that I was kind of saying that and got lost, and you pointed out correctly. If you're looking at an equation like that, at most, how many solutions are possible? Two solutions, right? So that argument has to be there. That is only true because it's a finite field. And I said that when we're going over the quiz problem, if it is not finite field, g to the m equals 1 may have more than m solution, right? So that's the key in here. At most two solutions, yeah. Yes, is inside the finite field, right? Inside the finite field. Therefore, it has more than one solution, it's still part of the inherited property. Yeah. Because it's a subset. All right, it's good. How about this one? Can you use that to show number of elements in a QP is p minus 1 over 2? All right, prove that. That's exercise 2. I don't know how to prove this one. You just explain to yourself. I thought about it. Maybe it's not worth it. We'll just look at each other. Isn't that obvious? And then shrug and move on. Give everybody two points and then move on, right? But I think the key thing is the surge activity. I think that has to be there. That part I think is the one thing to point out. If you have to say something, I will say that. This is a surjective map, isn't that right? Quadratic residue means something squared. It's coming from, everything is coming from this FP star squared. Right? So everything has two preimage, right? So the QP must be exactly 1/2 of the size. So FP star has P minus 1 element, right? Exactly 2 of them map to one thing. So P minus 1 over 2. That's at the end of the semester, we get tired and it says it's trivial. Right? Obvious. Get out of here if you don't get it. Something like that. All right. But it's good information to know that how many quadratic registers there are out there in finite field? P minus 1 over 2. If you list 1 through 11, only 10 of them, now only 5 of them, not 1 through 10, that's mod 11, only 5 of them are quadratic register. All right, this is an important thing. You'll see this a couple times. Let's get used to it. All right, here's it. I said it's an application primitive root. Here it is. B is a primitive root mod P, right? And then statement we're looking at is whether A is a QP. What is QP? Quadratic residue. When is this quadratic residue? Let's look at some statement. It's an abstract statement. Maybe it's not practical, but it all helps. If A is a primitive root to this exponent 2 times V, if there's a 2 in there, then it is necessary and sufficient that A is quadratic residue. And if you like log, you can look at it here, log, but if you don't like log, don't look at it. It's the same statement right there. You write A as a power of B because B is a primitive root. That exponent must be even number, right? Then it's a quadratic residue. If it's a quadratic residue, then the exponent is even. Okay? Let's prove that one. Here, exercise number 3, less obvious direction is that prove if A is a quadratic as you want P, then A is B to the 2B. See if you can prove it. Primitive root, that's the key. Maybe you're going to state the meaning of A being quadratic residue. What is the meaning of A being quadratic residue? Right? A is equal to, that's right. They use S, so let's write that S squared there. That's how it's not, right? Because A is a quadratic residue. So after you bring in this S, A equal S squared, how are you going to bring in the primitive root into the picture? Primitive root will generate everything is its own power. How about S? S is some element in there, right? So you can write S as power of which? You don't know it's a 2B, but definitely B down there, right? because b is a primitive root, right? So s is going to be power of v. How about that? Power of b, and that power is v. That's not controversial, right? Anything is a power of b, correct? Then you go back to that statement, a equals s squared. It's that simple. All right, that's okay? Yeah. Let's look at next statement. We're connecting the order of a, dividing p minus 1 over 2. 2 is the quadratic residue. But I listed it like this so that connecting this one is a lot easier, right? So here is exercise number 4. Prove if a is b to the 2v, right? Then that means it's a quadratic residue, correct? Yeah, quadratic residue. In that case, order of a must divide p minus 1 over 2. Order of a is really order of b to the 2v, isn't it? Yeah. Do you remember any formula about computing the order of a b to the 2v? There was this formula, right? B to the L. Here's the and b. If you have b to the L in general, right? What is the formula? Anybody remember? Order, right? Order of b, which is k, divided by GCD of L and k, right? Yeah. What is k in this case? P minus 1 because b is the primitive root. So put information to this statement and see if you can pull this one out. That's the idea. I don't know, about staring at this expression one way or another, we'll figure out, oh, that's Why? Well, so I just manipulate a little bit further. 2 and 2 is a common. So as I factor out of that GCD, I can pull out this p minus 1 over 2 that as is stated in that statement. So organized like this, p minus 1 right as a 2 times t. 2 is common, so I factor that out. Whatever this integer is, you can put it over here. Then p minus 1 over 2 is this order of a times the GCD of vt. So order divides p minus 1 over 2. Right? You'll find one way or another, just um, way to write it. Okay, so look, let's go back. Look at the statement. A being quadratic residue, and there is this primitive root statement. Its exponent must be even. And without primitive root any coming in there is a nice statement. Order of A must divide P minus over 2. Necessary and sufficient condition. Okay. So computing order of A still takes a bit of time, but it's not too bad. That's one concrete idea that does not involve primitive roots at all. So here's clever Euler kicks in. But have confidence you can prove this thing. Euler did it, but you're ready to prove it. So what is the exercise number? 5. So I want you to prove this one, exercise number 5. If a to the p minus 1 over 2 is congruent to 1 mod p, Euler claims that's quadratic residue. It's like a to the L is congruent to 1 mod p, right? What can you say about L? That's pretty much it. Right, if L is p minus 1 over 2, that's what we're looking at. A to the L is equal to, yeah, what can you say about L? Can someone come up with a true statement out of this? A to the L is congruent to 1 mod p. Something about L. Oh, then I know something about L. Order divides L. Order of what? Order of A divides L. Isn't that absolutely true? Yeah. So let's write that down. Order of A divides what? L. Now you stare at it. If nothing comes to your mind, I don't know. You can just stand against the wall. Yeah, that's what we just did, didn't we? Yeah? Right? Okay, yeah. A's in QP. Clever Euler, right? You raise to that half of these p minus 1, you reach 1, you know it's quadratic residue. Okay? What's exercise number 6? Second part, yeah. Exercise number 6. Prove it. All right. Yeah, it was a necessary and sufficient condition. If order doesn't divide L, then it's not quadratic residue. If it does divide L, it is a quadratic residue. No, if you square that, you go to the statement that is very insensitive of A. Is this true for all A, right? Yeah, that's why. Yeah. All right. Filling the Euler criterion. What's so good about it? What's so good about it? You don't have to compute the order. You don't have to know primitive roots, right? You just raise it to this Lth power, p minus 1 over 2. 1 or negative 1 tells you quadratic residue or not. Neat, yeah? Yeah. Yeah. It's not order of A, it's the order divides that or not. That's the statement. It's not the order. Yeah. But I thought you were asking this question. How do you know that it's 1 or negative 1? What if it is something else, right? Yeah, isn't that a possibility? I raise the p minus 1 over 2, then you get something other than 1 and negative 1, all right? So, yeah. Here in exercise, I'm going to make this one just the homework. It's not going to be exercise. It says if n is not prime, if 15, then corresponding version is that a raised to phi n divided by 2 instead of p minus 1 n divided by 2. And if it is 1, it still can be a quadratic non-residue. So this one really use not field structure, but primitive root structure. Because if p star has a primitive root, this is possible. Z mod 15 star does not have primitive root. Therefore, this criterion is not going to work. So it's very specific to prime. All right. So next question I have here is this exercise. I'm going to just copy this neat statement again. Euler's neat statement. All right, raised to that power, you know is a quadratic residue or not. But next question that Andrew was about to ask and then forgot is this. Why is a to the L is 1 or negative 1? What if it's something else, right? But this one says it's actually 1 or negative 1. And then you have to prove it. There's no other choice. A little bit tricky, but here's what I want you to look at. I think Keely already did it. Yeah, yeah, yeah. X equals a to the p minus 1 over 2, right? And then she squared it. That's the key. She squared it and observed that, oh, something's going on here. I have something to say. That's exactly what that conclusion. How'd it go? At most two. That's it. I have two. That's end of Euler's criterion. And here comes Gauss. He's looking at Euler's statement and then I can do something interesting here. So the Gauss kicks in. Again, it is about criteria, but in between there's a symbol. There's no result is introduced. It's just a symbol. All right. The symbol has been standard and it's useful. For that Euclidean like quick algorithm, we use the symbol. Right. Let's understand the symbol. There's no new concept. It's just denoting that A is in QP or not. They turn it into a different thing. Definition. For an odd prime, Legendre symbol for any integer A is denoted like this. A over P with a parenthesis around. This doesn't doesn't mean it's A divided by P, just a symbol. And we're mainly interested in these two cases, not the case A is divisible by B, but they define it to be 0. It's about congruence class of A being quadratic residue or not. If it is residue, positive 1. If it's non-residue, you assign negative 1, right? Why was positive 1 and negative 1? Where is this coming from? Previous one, Euler's criterion, right? That's exactly right. So you can see pretty much this is a to the p minus 1 over 2. How about that, right? Okay. Unfortunately, this is not equal symbol. It's just congruent mod p. This is congruent to 1 or negative 1, right? That is congruent to, is equal to that. But this is pretty much equal symbol. Okay? That's a symbol, and something nice is happening with that symbol. All right, this is just a statement. You can just look at it and nod and go, move along. That's that. All right, and P is 7. When A is 2, for example, 2 over 7, right? Is 2 quadratic residue or not? Mod 7. 3 squared 9. 9 mod 7 is 2, right? So 2 is a quadratic residue, right? So therefore we assign as 1 because 2 is congruent to 3 squared mod 7. So they put it in there. This is profoundly difficult question. Is 4 quadratic residue or not? Just kidding. 2 is square, so is 1. All right? Fair enough? Yeah. And these 3, 5, 6 never appeared. How many quadratic residues are there? No mystery. It's 3p minus 1 over 2 is the 3 of them, and the other 3 is a quadratic non-residue. Good? Yeah. Hmm. Positive and negative, yeah. Yeah. They're not quadratic. They're solutions that after you map it, the numbers in QP, not in FP star. Numbers in QP are called quadratic residue. So for example, if I'm looking at 2, the solution is 3, right? 3 is not called quadratic residue. 2 is called quadratic residue. So 3 and negative 3 maps to 2, right? But 3 and negative 3 are not called quadratic residue. 2 is called quadratic residue. So they're only half of them. Yeah, okay, good. All right. I already stated that, right? Makes perfect sense, don't you think? Legendre symbol agrees with the Euler's criterion. How about this one? Yeah, I think you can prove it. This is one of the neat thing about this Legendre symbol, right? If you multiply the two symbols, and then it becomes just that product of the symbol. Symbols, product of symbols is symbol of product. I don't know. All right, but this is a hint. If you replace that Legendre symbol with this Euler criterion expression, then it's just like one-liner, right? But it's still an exercise. What's the number? 8. Prime number. It's sufficient to show these two things are not equal. What am I going to do? Do you know what to put in between these two things? It's sufficient to show not equal. That's right, congruent to what? Mod what? Mod P. These are plus 1 and minus 1, right? Congruent to 1 and 1 and negative 1 and 1. That's the same thing, right? So you switch to that statement, and then you have a way to apply this one. Fantastic, right? Interesting thing is that if this is -1, what does that mean? A is a quadratic non-residue, right? What if B is, this is -1? B is a quadratic non-residue, right? Or together, they have quadratic residue, right? So it's interesting. Yeah, that's very interesting. All right. So this is called homomorphism, right? Homomorphism. It's multiplicative homomorphism. Yeah, you just count how many quadratic residue and count that determines that. Yeah. Here's the corollary. If here's what you're thinking, if I pick up one quadratic non-residue, right, and if you multiply quadratic residue to that, it remains quadratic non-residue, right, and then it covers all the quadratic non-residue. That is like I have particular solution. If you add homogeneous solution, you find all solution. Remember from a differential equation or just like a group theory. If I have a one particular solution, you add all the elements to the kernel, you reach all the preimage, just like that. If you have one quadratic non-residue, if you pair that with a quadratic residue, it remains quadratic non-residue. Not only that, it covers all the quadratic non-residue because of the number of elements. Same. Yeah. Yeah, it's an interesting structure. That's why in the earlier one, and I found 1 square root of 2 by just multiplying a to the square root of 2, you reach all the other square root in the finite field. There was a problem like that. So that's that as simple. I don't know. It's quite obvious you tried. Positive, -1. I'll leave that to you. Wow, this is interesting. That's something that I want you to try. I want you to look at the statement and see if you have seen this one before or not. If I change that statement to x squared plus 1 equal to 0, might be maybe you it rings a bell. P is an odd prime. -1 is a quadratic residue or not, like square root of -1, if and only if P is 1 mod 4. And I change the statement -1 being quadratic residue, x squared plus 1 congruent to mod P, solvable, right? Have you seen that? What theorem? Pew, W. Wilson's theorem, right? We found something. So that was the condition. Now, if Wilson's theorem didn't come to today, what do we have? Euler, right? We have Euler. What's the Euler theorem? Is this quadratic residue or not? Stick it into the Euler's criterion and see what this right-hand side is talking about. Right? Try it. Exercise 9. What's the number? I thought it's 9. No. Yeah, all right. All right. If it is, yeah, I think you should start with this is easier one. P is 1 mod 4. Y is -1 quadratic residue, right? What are you going to do? P is 1 mod 4. And you know the answer? What is it? Euler's. Euler's criterion, right? Euler's criterion. How does it go? Something is raised to P minus 1 over 2, right? What is raised to p minus 1 over 2? Negative 1. Now you have 50-50 chance. Is that going to be positive or negative 1? I see. No. Sweet. All right. So, negative 1 over p. What's the value assigned to this Legendre symbol? 1. All right. That's one side of the proof. Let's try the other one. If negative 1 is in there, quadratic residue, what are you going to do? That's right. Is congruent to 1, right? Mod p. It's fun. All right. Yep. Put it in there. Does it make sense? That was nice. Nice criteria. Any question? So summary here. Lemma, we started with the A being quadratic residue. We looked at the abstract statement. Primitive root, difficult to calculate, but it's in the middle of there. That's the meaning. Then we can pull out order condition using the order condition even better. Euler's criterion. No need to know the order or primitive root. Just raise it to p minus 1 over 2. 1 or negative 1 will tell you whether it's quadratic residue or not. And Gauss pushed this one a little bit further, right? And I realized that we can do that next time, tie it together with the proof of a quadratic reciprocity. But Gauss' lemma goes like this. A over P, Legendre symbol, is actually determined by negative 1 raised to, it's going to be plus or minus 1, right? Whatever this mu is, it's going to be even, it's 1. If mu is odd, it's negative 1. So Gauss recommend to count this thing, number of elements mu, it's a lot better than raising it to p minus 1 over 2 power. So it's a computation a little bit better. And we're going to cover that next time. Yeah, whatever that is, we'll do that next time. But it looks like this. And Gauss pushes it a little bit further. However, we do this quadratic reciprocity today. It's easy to introduce. So here it is. Skipping all that. This is the magic I was talking about. This is the Euclidean-like algorithm that speeds up the process of calculating this one so fast. All right, state it word by word. If P and Q are distinct odd primes, right? Both should be primes. Is Q quadratic residue mod P or P quadratic residue mod Q? Fun question, right? Who knew there was this fantastic relationship? This is just shocked Gauss, shocked all the prominent mathematicians in the 1800s. Everyone was thinking about this statement and what's going on. Not just proving it. People wanted to understand. Is this just pure accident? What is going on? It's quadratic modulus of P. That's right. It could be 1 or 1 and negative negative 1. Yeah. But here, only one exception is that if both P and Q are 3 mod 4, then they're opposite relation. If Q is a quadratic residue mod P, P is not quadratic mod P. and vice versa. If both P and Q are 3 mod 4, as you take the reciprocal, the quadratic residue property changes. That is a fantastic. Just Gauss himself gave like 9 different proofs of this one. He was fascinated by this, and modern mathematicians are fascinated by this phenomena. Make a whole book out of it. All right, let's look at the next one. Because these are odd prime, they have to take care of 2. Right? Is 2 quadratic residue mod P or not? And they have this simple answer. If P is 1 mod 8 or negative 1 mod 8, it's the same as 7 mod 8, right? Then 2 is always a quadratic residue. And if P is 3 mod 8 or 5 mod 8, 2 is always a quadratic non-residue. Simple as that. And this together is called quadratic reciprocity law, and then this is one called supplementary quadratic reciprocity law. All right? And here comes how it's applied, and you will like it. All right? This is quite easy to remember, right? As long as these two are not both 3 mod 4, you can flip it and it's the same value. Otherwise, you have to change the sign. And here comes. '83, it's not exercise. Maybe it's an exercise in the middle of the way, yes. 83 is a prime number. 103 is a prime number. Now, before you do the reciprocity, you can flip it around. 1 and negative 1 remains the same. The main question is that, is 83 quadratic residue mod 103? That's the question in here, right? And the reciprocity allows you to do the following. We're about to flip it, right? Okay, that goes like this. 103, 83, right? Why is there space? You have to check. Right. Is 83 3 mod 4? Kind of. Yeah? Yes. How about 103? It's 3 mod 4. So this is the exceptional case, right? So what should we do? If there's a quadratic residue, it's going to be, this guy is going to be negated, things like that. All right. Remember this question. Look at here. This is the fun part. 103 mod 83. We can reduce it. It's a congruence classes, right? 103 is a quadratic mod residue mod 3. Its reduced version is quadratic residue. That's the same thing. So what would you do? Yeah, knock it down. 83 going in there, right? So what do you have? 20, right? Just 20. Is that right? 20 is no longer a prime number. Reduce it. It's a 103 mod 83. That's what we're looking at. If 103 is a quadratic residue or not, mod 3 is the same as mod 103 mod is 20 mod 83. The quadratic residue property doesn't depend on any classes. So you can reduce that class. Now 20 is now prime number because you can factor it like this, right? But remember, AB over prime number, they split beautifully, right? It amazed Andrew, remember? 83. That's what I'm about to do. But we have to split it. We have to split it first. Now you haven't entered prime numbers, right? This is a prime number, 5. 4 is not prime number, right? But something nice about 4. What is it? 2 squared. So we already know the value. Negative 1 times 5 over 83. Isn't that right? 4 over 483 is already quadratic residue. Everybody knows 4 is squared too. So it's 1. So we're in here. So what comes to your mind? Flip it again. Now let's see. Are we in the situation of 3 mod 4 and 3 mod 4? It's not. So we can just flip it without touching the sign, right? It's the same thing. Now 83 mod 5. What can you say? Yeah, chop it down to the class. So what is it? 3 mod 5, right? This is easy now. 3 mod 5. Can you do that in your head? Mod 5 is 1, 2, 3, 4, right? Square them. What do you get? 1, 4, 9 mod 5, 4 again, this one, 1, right? So, is 3 quadratic residue or not? It's not. It's not in here. It did not occur as a square. It has to be in the bottom list. So, answer, -1. Isn't that right? End up at +1. So what is the conclusion? 83 is the quadratic residue mod 103. This is called what? Quadratic reciprocity. And this blew everybody's mind. Gauss was blown away, just like several years spending, come up with a different, and it inspired next generation to understand what's going on here. And it's all going to be presented on Tuesday. So don't miss it. That's right. And both of 3 mod 4. No, it's about when you flip these two things, the sign changes or not. That's where we use it. If you're in both 3 mod 4, you can flip this one, but you have to change the sign. 4. Right. That's right. Eventually. Yeah, eventually. This is very first thing we started, and the last value tells you is a quadratic residue. Yeah. So this is like exponentially faster to determine whether quadratic residue. So when we are solving this type of equation, like 2x minus 7 congruent mod, you know, 37, something like that, and you put it into a quadratic formula, right? And then you have square root of d, the discriminant. You have to determine whether this is solvable or not, right? How do you do that? That's right. Quadratic reciprocity. Apply there and show that this is solvable or not.